Good day and welcome to my YouTube channel. I'm Arthur Francis Divan. So I am the host. I will be taking us, it's a science-based platform whereby I'm going to be covering chemistry major and probably physics and mathematics alongside to compensate the whole reaction. We know too well that in science, chemistry does not exist on its own, alone. You cannot be a good chemist if you do not have a proper background or a very good background in mathematics. So as a result of that, I'm going to be bringing in mathematics as time goes on, especially the essential topics that will make up for what you need, like change of subject of formula, number-based system, fractions. These things are integral in the knowledge of chemistry as a whole. So today, we're going to focus on the preparation of reagent. We know too well, most of these chemical reagents like acids, bases that are being sent or gotten from the industry directly to be used in various institutions are concentrated. So for us to be able to make use of them as a chemist or as a technologist, you will be able to dilute them, which means you have to prepare them. So in the course of you preparing them, there are certain formulas which we ought to know or apply in the process of doing that. So, in terms of preparation, we have the solid and that of the liquid. Like acid, majority or most of the acids are in liquid form. So we have its own formula. So we have to look for the volume concentration. What volume of what you are preparing that will be used to dissolve in water in terms of what you're dealing with. And those of the basic, most of them, 99% of them are solid. So it also have its own formula, which we are going to apply. So today, we're going to begin with preparation of solutions, which are acidic solutions. So we have our formulas for that. So we're going to begin with the formula, then also apply the formula in terms of our calculations. So let's begin. So we have what we call the volume concentration. So the volume, let's use this. So we have our volume is often in cm cube. So for the first time, I'm going to write it down here. In cm cube, which is C for the molar concentration times relative molecular mass of the acid you're preparing times 100 all over the specific gravity times the percentage purity. So when we are calculating the volume concentration of acid, which are often in the, liquid form, this is the formula we're going to apply to do that. Not just acid. If you want to prepare the volume concentration for ammonia is in the liquid form, we apply this. So we use this basically for all solutions, liquid solutions. So the concentration will be required of you. If you are required to prepare 0.5 or 1.5 or 0.05, it is okay. The relative molecular mass of the compound you're dealing with, if it is HCl, you calculate the relative molecular mass times 100 over the specific gravity and percentage purity. These two are always enclosed or embedded in the bottle of the acid you are dealing with. If you look through the bottle, you see these will be given. But for the class purposes, we have to state these because we are not dealing with the various bottles of the substances or the solutions which we are going to calculate. So we have to state these ones, which is going to aid us. So I'm giving you an insight right now. If you were to be in your laboratory, you're asked to prepare 0.5 mole of HCl, you go through the bottle, look for the specific gravity which will be there, and the percentage purity which will also be written in the bottle. So with that, you can proceed to do what you want. So we begin with our first formula, our first question. It says that we should prepare 0.1 mole per dm cube of H2SO4. So this is our formula, like I said. Question number 1, it says 0.1 mole per dm cube of H2SO4. Now, from here, they will give us the specific gravity. Let me state it here already. percentage purity is 96. Our percentage purity is 96, and the specific gravity will also be given to be 1.84, which is 1.84. All right. Remember, the concentration here is 0.1 mole per dm³. The relative molecular mass will be gotten from the formula, and that is 100. Specific gravity is this. Where is it? It's 1.84, and percentage purity is this. So before we proceed in applying all of this, let us find out what the relative molecular mass is by our calculations. We know the relative molecular mass. Let's say this is H2SO4, which is tetraoxosulfate 6 acid. The relative molecular mass therein is hydrogen is 1 times 2, plus sulfur is having 32, plus oxygen is 16 times 4. All right. So this is 2 plus 32 plus, that's 64 or thereabouts. So let's find out what 16 times 4 is. Times 4 is 64. So this is my 64. So 64 plus 32, 60, 96 plus 2, 98. So I have 98 G mole for the relative molecular mass. So if this is it, then I can substitute these variables into this formula and I get what I want. Alright, let's get that. So our volume concentration is equals to, the concentration given therein is 0.1. So I have 0.1, let's call it mole per dm³, times relative molecular mass is 98 G mole, times 100 all over. Specific gravity is given to be 1.84 times percentage purity is given to be 96. So I have to proceed to multiply out those variables given so that I'll know what the volume concentration is. So now 0.1 times 98 times 100. I have 980, so I have 980 over 1.84 times 96 is 176.64. This is equals to 980 divided by 176.64 is equals to 5.55 cm³. Now, what we are having here is the volume concentration of 0.1 mole per dm³ of H2SO4. What we have, which is 5.6 or 5.55 approximately, is the value of the concentrated acid which we are going to measure out and dissolve in 1 dm³ of water. 1 dm³ is 1000 cm³. That is 1000 ml. Now, that 1000 ml, for example, if I don't want to waste my reagent because I have 5, maybe the bottle of the reagent, the stock is very expensive. I want to just prepare to know, maybe for titration purposes. What do? You can divide this, since this value is to be divided in 1000 ml of water. If you divide it by 2, means you dissolve it now in 500 ml of water, you see, and you still get exactly the same thing. You can divide it by 4 and dissolve it in 250 ml of water. You can divide it by 8 and dissolve in 125 ml of water, as the case may be, still retaining the concentration, the equivalent concentration of 0.1 mole per dm³ of the acid. So that can be done just to reduce or to save your reagent. You don't waste them. Probably if you need like 10 mil. Why would you prepare 1,000 mil by dissolving in 1,000? You divide it to the barest minimum where what will be left will not be a waste. You finish taking what you want and you discard the little one that will be left. Or you can put it and label it and keep it in your lab in case you may likely need it for future purposes. So that's our first question therein. Let's take our next question. 1.0 mole per gen cube of HNO3 of HNO3 trosonitrified acid. So the specific gravity will be different and every other thing. So let's begin. Our specific gravity for that is 1.42. Percentage purity is 70. Percentage purity is 70. Related molecular mass of this, hydrogen is 1 plus nitrogen is 14 plus oxygen is 16 times 3, which is equals to, I now have, I think that's 48. 16 times 3 is 48 plus 15. That will give me 63. So 63 G mole. That's the relative molecular mass. So applying my formula, the volume concentration therefore becomes the concentration of the acid, which is 1.0, times the relative molecular mass of the acid, which is 63, times 100, all over the percentage purity is 70, times the specific gravity is 1.42. This is equals to, so I have my 1 times 63 times 100. That gives me 6,300. 6,300. That's 6,300. All over, I have my 70 times 1.42. I have 99.4. 99.4. And this is equals to 6,300 divided by 99.4. I have 63.4 approximately. 63.4 cm3. So if this is what I get, 63.4 cm3, I'm to dissolve this in 1,000 ml of water to make it my standard solution. Now, because I don't want to waste my reagent, if, for example, you're carrying out a titrational class where there are a lot of students, it is okay. You dissolve, measure this concentration, dissolve in 1,000 ml of water. Okay? But for the purpose of not wasting your reagent, maybe there are just 2 or 3 students. You can divide that value by 4 and you have 15.8. That 15.8, you dissolve it in 250 ml. You see that? That saves you most of the reagent which you should have used. Because if you use 15 instead of 63, you see that you save a lot of the stock solution. So it's a way of preserving your reagent, not wasting money. Let's take another question. 1.0 of phosphoric acid, which has 90% purity and 1.75 specific gravity. 1.0 of that. Okay, let's take this out. Okay, we have our phosphoric acid, which is H3PO4. Specific gravity is 1.75, 1.75. Here is 90. As the percentage purity is 90. Okay, let's calculate the relative molecular mass of that. So hydrogen is 1 times 3 is attached to it, plus phosphorus is 15 at atomic mass. The relative molecular mass, check the relative molecular mass of phosphorus, which is supposed to be 30 or thereabout. 30. So we have 30 plus oxygen is 16 times 4. Alright, this will go 3 plus 30 plus 64. 94, 97. So this is 97, the relative molecular mass in G mole. Alright, if that is true, now I have this to be 97. Let me take out most of this to save space. So I have 97 G mole here. Applying the formula, the volume concentration becomes the required concentration, which is 1.0, times the relative molecular mass, which is 97, times 100, divide by specific gravity is 1.75, times percentage purity is 90. Take note, it mustn't be percentage purity for this or the other way. I can use any one interchangeably. I can use specific gravity times percentage purity or percentage purity times specific gravity. It doesn't matter. So anyone can go. So if that is done, what are we going to get? We have 1 times 97 times 100, which is 9700, divided by 1.75 and also divide by 90. We have 61.6. So this is 61.6 cm cubed. This is what we are going to dissolve in 1 dm cube of water, which is 1000 cm cube of water, or 1000 ml of water. Divided by 2, you dissolve in 500. Divided by 4, you dissolve what you get there in 250. Divided by 8, whatever you get there, you dissolve it in 125 ml. Don't forget that, it is important. Okay, let's take another one. The fifth question, let's take to prepare 1.0 mole of ethanoic acid. So do not forget, do not be surprised that we're using 1.0 mole per dm cube. It can be 0.5 mole per dm cube based on what is given to you. It can be 0.1 mole per dm cube if that is what is given to you. It doesn't matter. We can calculate them all over again. Like we've used this, we can use 0.1 mole to do the same thing. We get something different from what we used in the previous. So that's how we go. Now let's take that of ethanoic acid. Okay, here we have CH3 COOH here. This is for ethanoic acid. Okay. Let's take out this. Specific gravity becomes for ethanoic acid. The specific gravity is 1.05. 1.05. Percentage purity is 99.5. Wow. 99.5. And relative molecular mass we calculate of base. Carbon is 12, plus hydrogen is 1 times 3, plus carbon again is 12, plus oxygen 16, let's call it times 16 times 2 if I want, because there are 2 of them, or 16 plus 16, then plus hydrogen, which is 1. Now I move on. This is my 12 plus 3 plus 12 plus 32 plus 1, that's 33. Now, you can use your head to do that, but I don't want to waste time. So I have my 33 plus 12 plus 15. That gives me 60. So the relative molecular mass of ethanoic acid is 60. So I can take out the other guys. So this is out. I have my 60 here. Now volume concentration becomes the concentration of the required which is 1.0, times the relative molecular mass, which is 60, times 100, which is in the formula, all over the specific gravity, which is 1.05, times percentage purity, which is 99.5. This is equals to what? So I have 1 times 60 is 60, of course, times 100, which is 6,000. Divide by 1.05 and also divide by 99.5. 99.5. That gives us 57.4. 57.4 cm3. Don't forget I said earlier on, this value is huge. If I want to carry out a personal research, my own personal research, I'm going to find out something about ethanoic acid, probably 1.0 mole per dNq of ethanoic acid. I do not need to measure out this kind of big value, 57. I'm going to finish my reagent. So what do? I divide that by 4 or by 8, if possible. I divide that by 8, and I have 7 cm3. That 7 is what I should measure and dissolve in 125. And I can use that to save my reagent. I kept repeating this, saving your reagent, quite often, because many a time as a chemist, you are going to be embracing kinds of reactions or preparations in the lab, because you can't do chemistry without entering the lab. You're going to measure or merge the two, the practical aspect and the theoretical aspect. Probably in your final year when you're carrying out your thesis, you ought to do these things yourself. You have to know how to prepare your reagent. And probably when you start in school too, in your year 1, these things should be taught, are meant to be taught. So it is for our safety purposes that I have to bring to our knowledge once again the basic fundamental principle which we need as chemists anywhere we go, that we can apply to survive, to show that actually we are potential chemists. So let's take our 6th question. Probably we can solve like 7 or thereabout for the day. With that, I believe we will be able to measure or understand quite very well how to survive in terms of preparation of reagent. Let us prepare 1.0 mole per dNq hydrofluoric acid, HF. Now, hydrofluoric acid is a very concentrated acid. It is not used in the laboratory where students are because it's very powerful, highly concentrated, but it is not the strongest. Let's put it that way. The strength of acid is measured by its, when we check our acid base and salt, we say that acid, tetraoxosulfuric acid, is the strongest acid. Okay, but it's not the most concentrated. Okay, because it has 2. For example, we have our H2SO4, but this is monobasic, this is dibasic. So somehow, how do we measure the strength of the acid? It is based on its ionization power, how it ionizes to give us, this will give us 2H plus SO4 2 minus, but this will give us H plus F negative. Now the ionization strength of the acid of tetraoxosulfuric acid is far higher than that of this. So it is based on this principle that we say H2SO4 is the strongest known acid compared to any other acid because its ionization strength is 2. But this is more powerful in terms of reactions. We use it in the industry to melt stones. That's to tell you how powerful it is. If it touch you, even the bone will not be seen. So it is because of that toxicity or the strength or that powerful corrosive nature of it that it is devoid in being used in the lab, where students are there to practice how to do these things. But we use them in industries, fine, but not in the classroom because it's too powerful. But based on the strength of acid, we say this it's more powerful than this in the strength because of its ionization power. Alright, so now hydrochloric acid is what we want to determine 1.0 mole of HF. So let's take our HF here, although you're never going to prepare it in your lab. I don't even think if you're ever going to see it. Because in the various institutions, higher institutions of learning, they don't get them for you. So I have 1.13 specific gravity. 1.13 percentage purity is 40. Yeah, is 40. Relative molecular mass is 1 plus fluorine. What's the mass number? Hydrogen, helium, lithium, barium, boron, carbon, nitrogen, oxygen, fluorine. 9. Is that 18?
18.9.
18.9. So let's take 19. Alright. Let's call it 19. So if this is it, and we have to put these into use, we have, first, the concentration required is 1.0 times the relative molecular mass, which is 9. Oh. Say it again. You say is 18.9 plus 1. That's 2. 18. That's 19.9. 18.9. So we call it 19, Abi?
Yes.
Plus the 1.
It's 20.
Let's take 20 there. Or 19.9. Better. Alright? So 19.9. So multiply by 19.9 times 100 all over what do we do? Specific gravity, which is 1.13 times 40. So let's see what we get here. 19.9 is times 1 is still the same. Times 100 divided by 1.13. So divide by 40 is 44.02. So we have 44.02 cm or 44.0. In chemistry, our answers, even if we aren't told, should be in 3 significant figures. So 02 make it 4, so just leave it at this. So now this value should be measured and dissolved in 1000 cm3, or divided by 2, put it in 500, or divided by 4, put it in 250, or divided by 8, and put it in 125 ml of water. So by so doing, that is prepared. Let's take maybe our last question for the day. Yeah, could that be the last? Okay. Let's prepare 1.0 mole per dm cube of ammonia. NH3, 1.0. Relative molecular mass, we're going to calculate that. But the specific gravity is 0.88. Percentage purity is 35. Relative molecular mass is 14 plus 1 times 3, which is 3 plus 14, which is 17 gmol. Now, the reason why I have to add ammonia is a base, okay? Ammonia gas, in short, it is the only alkaline base. Or, sorry, let me put it this way, it's the only alkaline gas. All basic are always solid, but this is the only one that is a gas. Alright, so by so doing, the reason why I'm adding it here, because what I've been calculating or preparing, what we do so far have been acids all along. So do not think that the formula can only be used when you're dealing with acid. You can use it while dealing with a base, provided it is in a liquid form, or whatever substance that is in a liquid form. Even mercury is in a liquid form. You apply this, use it. Alright. Now, using our formula, the volume concentration becomes the required concentration, which is 1.0, times relative molecular mass, which is 17, times 100 all over Specific gravity is 0.88 times percentage purity is 35. This is equals to, what do we get here? We have 17 times 100, which is 1700, divided by 0.88, and then divide also with 35. We have 55.2. So 55.2 cm cubed will be the required volume that should be measured from your stock bottle, which is concentrated, and dissolved in 1000 cm cube of water, distilled water. Or you divide it by 2, dissolve it in 500, divide it by 4, dissolve in 250, divide it by 8, dissolve in 125, as the case may be, based on what you want. If you're dealing with a big class, you don't need to divide it, just make use of the 55.2. So far, what we've done here today is to show us how to prepare our stock solution from the concentrated ones gotten directly from the laboratory. Because of their concentrated form, we are required to apply our formula, which is the volume concentration, to reduce the concentration to what we can handle. We say concentrated forms of acid are corrosive, but the diluted form is not corrosive. So you see why we have to prepare it to have it diluted. And when that is done, don't forget, we always put acid into water and not water into acid. When you're done preparing, you measure the required amount of acid and pour it into the required volume of water. Do not make the mistake of using water, pour into the acid. It's going to splash on your face. So far, we've been able to determine that this is for solutions. Now, probably in our next class, we're going to be dealing with solid, where we use a different formula for preparing that of solid, which is the mass concentration, is the required concentration that should be dissolved in our solution, which is either 1000 or 500, the case may be. I have a lot of questions on that, a lot of them, so I wouldn't want us to start somewhere and not finish them. So we're going to take this in a separate class of its own. But remember, that has to do with GDNQ equals to the molar concentration, which is 1.0 times the relative molecular mass of that particular compound which you're going to be dealing with. Whatever you get there becomes a mass concentration of that base or that solid substance, which is also in its concentrated form. So when we do that, we dissolve it in 1000, which is now diluted. Then thereby, we can use it in the laboratory for our various calculations or anything we want to produce. So this is what it is, the elementary aspect of our reagent preparation that we need to know, we must know. We can't survive without this, so it's basic. So it's a pleasure to be with you. I look forward to have more classes with you, exposing the essential areas which we need as chemists. So do have a wonderful time. I see you when I see you again. Thank you.